Right, hey everybody, welcome back. Hopefully another short video from me today. I'd like to cover radioactive decay and what it means. You probably already got a good idea what it means from the previous videos we've looked at. Uh, a radioactive decay is the process of going from an unstable uh, radioactive atom, to a stable or at least a more stable atom. If that involves the release of alpha or beta particles, you already know that involves going from one atom to a completely new atom. The reason I've started with that is that I think there's a misconception that, and hopefully it's not, I'm not going to fuel that misconception by the little animations I've got in my presentation here, but there's an idea that decay means you start with a radioactive atom, it decays and it disappears. There's no disappearance of atoms with decay. To do that, you'd need, basically a nuclear bomb. So we're not talking about that. We're talking about the decay of an unstable atom into a more stable atom. Okay, it's probably a good idea as well to just talk a little bit about where all this radioactivity is coming from. And it might surprise you or shock you to know that you're being hit by alpha, beta, and gamma every minute of every day of your lives, because we're surrounded by radioactive sources of or radioactive materials, radioactive sources. It's not an issue as long as the dosage isn't so high. Basically, it's not going to cause any harm, or any harm that is caused, the body can repair itself. It becomes dangerous when you're being hit by a big dose of radioactivity over a short amount of time. So there are a few interesting sources. One is that you're being hit by basically gamma rays from space every minute, and sometimes more at higher doses than others. Another source, if you live near a hospital, nuclear medicine is a real growing field in modern medicine. So hospitals are using radioactive sources all the time and disposing of those radioactive sources. So if you live near a hospital, you're more likely to have a higher dose of radioactivity. Another source, well, there has been a huge number of nuclear bomb explosions from the 1940s onwards. I can't remember exactly how many, a few hundred, I believe. All of that radioactive fallout has gone somewhere. And where's it gone? Well, basically, it's fallen back to Earth in the form of rain or dust, and it surrounds us in our water and in our soils, our rocks, all around us. But as long as that dose is small, it's not going to cause any problems. All of the waste that was blown out of the reactor after the Chernobyl accident in 1986, the same thing happened. It had to go somewhere. It largely fell to Earth over Eastern and Northern Europe. So there are some parts of Europe, obviously especially close to the explosion, where the soil is much more radioactive than in other places. Again, as long as the dose is small, it's not a huge problem. Another interesting one is radioactive sources just occur naturally. In the north of England, where I'm from, especially in Yorkshire, where I'm not from, there are basically rocks that naturally contain radon gas. And when people over time have built houses there and dug down into the rock to create foundations or basements in the houses, they've released this heavy gas that kind of lingers and hangs around. And it's evident in some villages and towns in Yorkshire especially, there are big spikes of cancers and tumours higher than what you'd expect the natural average to be, and that's because of this release of naturally occurring radon gas. Right, so let's move on. I want to show you a couple of animations. I hope it doesn't cause any kind of misconception here, because I've got, if I show you this this animation, these atoms are going to disappear from the screen, and obviously we've already said this, radioactive decay doesn't involve the disappearance of atoms. You need a nuclear explosion to do that, or a nuclear bomb. So if I play this animation, so over time, you can't say at any one point of time which atom is going to decay, but you do know it occurs at a certain rate. And that rate is different for every radioactive element. Let's call this one smithium, after me. It doesn't really exist. So you know over time how long it's going to take for half of the atoms that are going to disappear, how long it's going to take pretty much for all of them to disappear, because you know the rate at which they're going to disappear. But you can't put your finger on one of those atoms at any one time and say, I know that at that instant in time that's going to disappear. You could think of the radioactivity as being just one big block of radioactivity like this. The one thing we've not actually talked about is units of radioactivity. I did mention actually one unit called the becquerel. Another unit is the Curie, named after Marie Curie. Another unit is the rad. The unit that you can expect Cambridge to give you in the exams is a very simple unit called the count per minute, or maybe the count per second. That basically means if you're standing there with a Geiger counter, how many alpha particles or beta particles or gamma rays are going to hit you per minute. If one alpha particle or beta relates to one decay, that equates the number of decays per minute or per second. So let's say we've got one block of radioactivity here. Again, this is smithium. I know that after a certain amount of time, half of the radioactivity will have, or half of the radioactive atoms will have disappeared. After the same amount of time goes past again, another half will have disappeared. After another amount of time, another half, and so on. That's measurable. I can't say again at any moment in time which atom will decay, but I know that after a certain amount of time, half of the atoms I started with will have decayed. If that same amount of time goes past again, I know that another half will have decayed, and so on. We'll come back to that, but if you can see above my head the kind of conclusions from this, you probably realised that the amount of time that it takes for half of the radioactive atoms you started with to decay will be called the half-life. It's the time it takes for half of the original set of atoms to decay, and so on. And each radioactive element has a different half-life. Okay, so let me move on again. Probably it's not an analogy you want to hear, but we could talk about this in terms of the spread of a virus, let's say the coronavirus. So let's say we start with one person here. This person has the disease, and over time, that one person will infect another two people. After the same amount of time goes past again, those two people might infect another two people each, which means we've now got 4 people infected. Same amount of time goes past again, those 4 people now infect, not the best diagram, 8 people, and so on. So we've gone over time, we've gone from 1 person infected to 2 people to 4 people to 8 people. And if I'd carried on, if I'd space, we would have gone from 8 to 16 to 32 and so on. So you can see this is not a linear increase. We're not going from 1 person infected to 2 people to 3 people to 4 people to 5. We've got a doubling each time. And this doubling is called an exponential, if I spell this right, an exponential increase. In other words, it's logarithmic. It's doubling over time. It's not linear. This relates to what we talked about in a certain way, except in this case, it's an exponential increase. In radioactive decay, we're going from a starting point of, well, let's say here, 8 atoms, and then after a certain amount of time, we're going backwards in time to, well, let's say 4 atoms, back again to 2 atoms, back again to 1 atom, and eventually in this model we'll go to 0 radioactive atoms left. So I hope that makes sense. In terms of the increase, an exponential increase, we could draw a graph very roughly. Let's say this is time in, I don't know, minutes, and let's say this is infected people. You might have realised the graph would look like this. It would start off shallow, double, double, and double, and that would be an exponential increase. However, we already said that what we're looking at with radioactive decay is not an exponential increase, it's going to be an exponential decrease. So I can show you that on the final slide I've got here. This is the graph you'd expect from an exponential decrease. Here's our smithium atoms. Let's say we start with 500 atoms at time 0. After a certain amount of time, it will have halved. If we start with 500 atoms, we can see the time it is when it will have halved. So if we start with 500, after a certain amount of time, we'll have halved it. We'll have gone to, hopefully I can draw this okay, without a ruler. We'll have gone to 250. We can draw a line over to the graph, and we can draw a line, this is very difficult here, a line down from the graph. That time there is a very special time. It's the time it's taken for half of the atoms to disappear. And we've already said here, that is called the half-life. So the half-life of smithium, I can see from my graph, is approximately, well, that looks something like 7 minutes, I guess. 7 minutes. If another 7 minutes goes past, and we go from 7 minutes to 14 minutes, that's another half-life, and I can see here, then we've gone from about 14 minutes. In 14 minutes we've gone from 250 to half of 250, which is about 125. So that's the half-life, and that's the graph we expect from exponential decay. So if I just return to my my conclusions up here, hopefully from this lesson we've got 4 points. Number 1, a decayed atom doesn't disappear, it just turns into a more stable or a stable atom. Number 2, as we go through time, we have a kind of graph called an exponential decay curve, or an exponential decrease, or an exponential decay. 2. Number 3, every radioactive element in the universe has a different half-life. I did just write down a few of them, they vary a lot. Francium, radioactive element, has a very short half-life of about 22 minutes. So if you start with 500 atoms of francium, you know that after 22 minutes you've got 250. Einsteinium, interesting element, I'll leave you to guess who it was named after. The half-life of Einsteinium is 471 days. Then you go to something like uranium. Uranium has a half-life of, believe it or not, 230 million years. Very long half-life. Which is part of the problem of dealing with uranium waste from nuclear power stations. It hangs around for a very, very long time. We'll come back to these half-lives when we talk about the uses of different radioactive elements. So there you go. I hope that made as much sense as I could make of it. I hope it wasn't too boring. I hope you're dealing with quarantine okay. As usual, I'll sign off by saying hopefully I'll see you in a few weeks, although maybe that's turning into months at the moment. Okay, take care everybody. I'll hopefully see you soon. Goodbye.